LPNS Scalable and Latency-Predictable Local Storage Virtualization for Unpredictable NVMe SSDs in clouds. First, it is the outline of today's presentation. First, I will introduce the background and motivation of our LPNS NVMe virtualization research. Then I will introduce the scalable architecture and some key components of our LPNS design. I will introduce some implementation details of our LPNS artifact. And in the evaluation part, we use both micro benchmarks and some application benchmarks to demonstrate that LPNS can provide very reliable latency predictable QoS control for both virtualization scenarios and real-world applications. Finally, we will discuss the overhead issue of our LPNS and conclude this presentation. First, let's move to the background parts. Our LPNS is an NVMe virtualization mechanism. So we first introduce NVMe specification. NVMe is efficient and scalable interface designed for the high performance SSDs, which are widely used in clouds and some personal computers. The NVMe specification can provide high throughput and microsecond level latency performance, which is much better than the traditional interface such as SATA. And the high parallel SQ-CQ interactions between the host OS and the SSD controller is the most significant interactions when we try to develop a NVMe virtualization mechanism. There is another part background. We will introduce the two solutions for the cloud instance storage resources. The first solution is to use the remote storage pools or dedicated storage servers. This solution is very efficient, scalable, and portable in the large-scale data centers. There are also many famous related works, for example, Reflex, libIO, and some famous commercial products such as Malloc Snap. Besides this solution, there is another local storage resource solutions which let the cloud instance to use the local storage from the SSD on the native service. This solution may have three main advantages. The first is it can remove the additional bottleneck of latency performance which are incurred by the network devices and the complicated network topologic in the data center. And the third is it can remove the expensive costs for buying the expensive network devices. And the third is the solution is more friendly to the tenants who want to buy a bare metal cloud storage, since these tenants want to build their own cloud infrastructures and they do not want any conflicts with the remote storage cloud infrastructures. For the local storage solution, there are many related works, and most of them are the storage virtualization results, storage virtualization solutions, and the most advanced software implement NVMe virtualization are SPDK and MDEV NVMe. And recent years top conference has proposed some hardware and software co-designed NVMe virtualization mechanism, for example, FAM and BM store. And then we move to the motivation of our LPNS research. analyze the current storage virtualization mechanisms, and we find that some limitations of them. First, we think that the current virtualization only concentrate on high performance, and they are not very efficient in in achieving latency predictable QoS control. And this storage virtualization cannot accurately monitor or prospect the multi-tenant workloads with different QoS requirements. And most important is they cannot bypass the device-side latency interference. The device-side latency interference issue refer to a phenomenon that when multiple VMs with the virtualized NVMe storage shares the same underlying NVMe SSD. The throughput-intensive VMs will generate a large number of NVMe I/O commands to compete for the NVMe I/O queue resources, and it will result very serious congestion on the SSD controller, and it will cause the latency degradation and unbounded latency of the VM with latency-sensitive workloads. We use a typical case to introduce this phenomenon. There are two VMs sharing one Intel Optane SSD, and the VM1 run light but latency-sensitive data I/O workloads, and it has a 30 millisecond SLA. But VM2 run throughput-intensive workloads without any latency QoS requirement, and its workloads arrives with burst. We find that in this figure, we find that the throughput-intensive workloads in VM2 will cause a very serious latency degradation of VM1 workloads, and VM1 misses its SLA. And this is very unacceptable to the cloud tenants. If we further study the device-side latency interference, we may find that the more intensive the competitive workload is, the more serve latency interference will happen. This phenomena happens in all this the state-of-the-art NVMe virtualization, including SPDK, SRV, and MDEV NVMe. From this figure, we will find that with the increasing IOPS of VM2 workloads, the VM1 will face more serious latency degradation. We further analysis the VM latency distribution in different phases, we may find that the average latencies on the NVMe controller grows from about 60% to over 90% with the increasing IOPS of VM2 workloads. This can show that the control of the unpredictable NVMe SSD is the bottleneck of the device-side latency interference. And we can also find that even the hardware-software co-design virtualization, they usually use an accelerated card, no matter SmartNIC or FPGA, to attach the standard and unpredictable NVMe SSDs. They cannot bypass the device-side latency interference. If we further analysis the storage I/O QoS researches, most of them do not concentrate on the virtualized device. We may find that among all these related works, Q2 is the state-of-the-art latency control storage QoS systems. However, if we let multiple competitors to compete for I/O resources against one latency-sensitive workloads, the K2 can provide reliable latency control, but it will cause a very serious total throughput loss. For example, it will result up to 2.27 GB per second throughput performance loss on the Intel Optane SSD. So it is unacceptable for the cloud vendors. Our LPNS is optimized for the virtualized storage scenarios, and it can provide a predictable latency QoS control, and it will save more throughput against K2. We will further introduce the LPNS design. LPNS has a very scalable architecture. It supports the hybrid deployment of host process, containers, and VMs on each single NVMe SSD. The host process and the containers can use the original NVMe model to access the SSD, and we also design an LPNS model to cooperate it with the original NVMe driver model. And for the VMs, all the VMs will have 4 virtualized storage devices, and each device has the 4 NVMe feature. And inside LPNS, it has a self-feedback QoS control. For the VM with latency predictable QoS, we call it SVM. And for the VM without latency predictable QoS, we call them IVMs. The LPNS can monitor their workload and performance data to perform the self-feedback QoS control. Finally, LPNS optimized the polling design over the traditional software implement NVMe virtualization mechanisms. It also used the active polling for I/O processing accelerating, but it can flexibly configure the numbers of the polling threads. For the IVMs, we only use one thread for all the IVMs, and the one thread can utilize the high throughput. And for the SVM, we can use one dedicated polling thread for better latency performance. LPNS design also has some key contributions in developing scalable IO queue handling. Now it has an hardware queue pool, which can allocate any numbers of hardware queues into the pool, and let a queue scheduler to manage the time division multiplexing of the queue resources. In the hardware queue pool, there are 2 kinds of hardware queue. First is the one-to-one queues, which can only bind it to one virtual queue of one virtual machine, and this will help to achieve better latency predictable QoS control effect. And the left are the one-to-n hardware queues, which can be shared by multiple virtual queues. Also, LPNS design L command throttling by following the DNC modeling. The DNC modeling is a deterministic queue systems with a deterministic network calculus. In our current work, we concentrate our problem model by concentrating on the 4K block size random read and write. And if we concentrate on the scenario where there are J IVMs co-corresponding with I IVMs, we can get the arrive and service curve as below, and we can use the model to get the latency upper bound. So for the SVM, it uses one-to-one hardware queue, and it can use dedicated polling thread for better latency performance. And it will face no I/O command throttling and no throughput sacrifice. And for the IVMs, they may use the left and idle I or idle one-to-one hardware queues and share the left 1 to n hardware queues. And all these IVMs will share the one polling threads for better saving of the CPU core resources. And the IVMs may face dynamic I/O command throttling, so it may face a little bit throughput sacrifice, but our evaluation can show that the sacrifice is much smaller than the previous work K2. LPNS implementation are included in Linux kernel source code, and now the current version is based on Linux kernel version 5.0, and we can integrate it LPNS into higher 5.x version. We did not bring any changes to KVM and QEMU, so any version is okay. An LPNS implementation is based on media pass-through, so the new implemented kernel model NVMe mdev.ko model is cooperated with the VFIO mdev support of Linux kernel. The new developed kernel model, including the admin and IOQ resource management and polling effect for performance detection, optimization, and I/O throttling. And we provide a kernel config for the cloud system maintainers to turn off the LPNS configurations. LPNS can work on the mainstream Intel or AMD CPUs and all the commercial NVMe SSDs. So it will bring no purchase cost of the SmartNICs or FPGAs. And finally, is the LPNS evaluation. The evaluations are based on two servers. One has an Optane SSD, and another has an SRV capable Samsung SSD. The micro benchmark is using the FIO benchmark to generate a 4K block size random read or write. And we compare LPNS against the VirtIO SBDK vhost block and MDEV NVMe on the Intel Optane SSD, and we compare LPNS with MDEV and SLV on the Samsung SSD. The application benchmark has two parts. First is we replace the web user service of the open source product systems, and we also generate use YCSB to generate workloads on a RocksDB database. The micro benchmark results on Intel SSD prove that the LPNS can achieve up to 11.5 and about 3 times latency optimization over SBDK and MDEV NVMe. The results on Samsung SSD prove that the LPNS can reach up to 18 times latency optimization over SRV. If we increasing the numbers of the IVMs, we may find that the LPNS can achieve up to 7.4 latency optimization of MDEV NVMe, and it can bound the latency at 15 milliseconds. In the application benchmark, we first replace the web user application. We may find that the evaluation has 4 VMs sharing the same SSD, and 1 is the SVM, and the 3 IVM as competitors. From the SVM workload, we can find that the LPNS is the best among all these storage, NVMe virtualization and storage QoS control. The evaluation results on Intel SSD is similar, and LPNS is still the best among the related works. When achieving a good latency predictable QoS control, we also concentrated on the total throughput performance of the different virtualization storage. We can find that LPNS can increase up to 1.45 times of additional total throughput over K2, and this part of throughput is equivalent to nearly half of the maximum throughput of the entire Optane SSD. And if we increase the numbers of IVMs on the Intel SSD, we may find that the LPNS can get better latency bound than the state-of-art mechanism K2. Finally, the application benchmarks of YCSB on RocksDB, we also find that the LPNS can achieve up to 7.4 latency optimization over NVMe MDEF in YCSB. The LPNS may need some latency predictably trade-off on different NVMe SSD, since different NVMe SSD have different serve curves, and most NVMe SSD may have poorer random write performance than random read. So using a YCSB for them may waste more total throughput in random write than random read. The performance and resource overhead of LPNS is much smaller than traditional software level virtualization, because we design flexible and scalable polling mechanism, and the performance and the workload detection in the kernel module is periodical, so it will save the kernel memory resources. We conclude our LPNS works. We may have three main contributions. We first analyze the device level latency interference and argue the importance and capacity to overcome this interference from the OS level storage virtualization. And we design LPNS, the first OS level NVMe virtualization solutions with latency predictable QoS enhancement, and we implement LPNS in the Linux kernel without any further purchase of the SmartNICs or FPGAs. And that's all for today's presentation. Thank you.